stems from three different parts. That is computer vision, computer graphics, and we've seen some examples.
Not that I really want it.
And now we're going to go to optics.
You can have it.
Markus Testorf, one of the co-chairs of the conference, will now give a tutorial on PhaseSpace Optics, which I think in the design of computational cameras will get a more and more important role. So Markus got the PhD from University of Erlangen-Nuremberg, and he's now has a position at Darmstadt. And I'm looking forward to the book.
Yes, that's why I have a tie. Well, thank you for this introduction. And while this computer is coming up, I may be entitled as a co-chair of this conference to a remark. I think this is really a small conference, but I think you have every chance to enjoy a very exciting program. I think most of the credit for this goes to my two co-chairs. For me, it was really a very smooth ride. I just jumped the bandwagon and piggybacked along. What is exciting is this opportunity to talk about something that I think is really exciting, and that is PhaseSpace Optics. I usually don't like missionaries, but this is something that has occupied my thinking for almost 2 decades now. And I think just the fact that I like this kind of topic has made me some sort of missionary. So what I would like to do today is I like to try and convince you that phase-space optics is something useful for your profession. Well, this is apparently not working, so I have to stand here anyways. So what is phase space? Probably it is something that you have come across in one way or the other. If you are working in my field of research, that is physical optics, geometrical optics, you open any of the introductory textbooks and you will find the ABCD matrix optics formalism, and that's just phase space in disguise. You may come from signal processing, and you're probably familiar with joint time frequency transforms, or maybe wavelets, and that is something that has a substantial overlap with what I call phase space. Then in this conference there are several contributions that deal with optical light fields, and again there is something very common between optical light fields and phase-space optics. And in physical optics, terms like the Vigna distribution function and Vigna Optics have become sort of part of the terminology. So why is it necessary to have a new term, phase-space optics? And I really strongly advocate this term. The reason is that when we think about signal processing, image processing, that's a bit like a Cinderella's task. We sort of have a signal, and we don't want all of this. We want to get rid of the noise, and we have some prior knowledge what we want, and then we take any means that we have to extract what we need. Sometimes this is very ad hoc and may work or may not work. When we talk about the light fields, there's already some idea about how light actually propagates as a ray. But if we want to sort of bring things together so that we can talk simultaneously about geometrical optics, wave optics, partial coherence, then we need a model of these configuration spaces that really carries the physics of light propagation through regardless what kind of model we are using. And that's precisely what I call phase-space optics. Why phase-space? Because much of the mathematical foundations, they are borrowed from theoretical physics, from classical mechanics and quantum mechanics. We do not have to deal with this here today, but that is a reason for the terminology. So phase space emphasizes the physics of the problem. And I guess thinking about the community here, probably that is part of what I need to do today to convince you that it is a good idea to think about the physics. Why? Because if you understand how light propagates, you may have a better understanding which part of the signal you actually want to extract. Here's a little bit of my personal history. The first paper that I actually published on phase-space optics dates back to 1995. And back then it was something that I think most of my colleagues considered a very, very esoteric way to think about physical optics. I mean, you would go to a conference and people would express curiosity but essentially ask, well, what is it? Do I really need to know this? And so for that reason, it has remained more or less a hobby of mine for quite a while. And it is just during the past few years that I haven't moved, but things have come along, and now I feel like I'm in the center of the action. Pretty much every development in imaging technology has some connection with phase-space optics. And sometimes I think, well, now I do something completely different. I want to think about other problems, and invariably I come back to this. So this is exciting for me, but I also think it is important to sort of disseminate knowledge about this. And I have to say that I may be mistaken, but I date sort of the beginning of this rapid development back a few years to a workshop that took place at the University of North Carolina in Charlotte, where people came together to discuss super resolution and image processing applications. And we had some people from the computational photography community, including Mark Levoy and Fredo Durand, and they sort of told us how much they already use phase-space optics in a way. And now I'm here and return the favor, talk about sort of the ideas that we have in the optics community. Do you really need to know this? I would say no. If you are comfortable with what you're doing, you probably can live without this. And I have to be also honest that if you really delve into phase-space optics and you really want to know what's going on, you may encounter heavy mathematics. And it may be intimidating. I do not want to talk about this mathematics today. I want to convince you that a little investment yields big rewards. That's as far as I can go today, and that's as far as I want to go today. So I would like to take these different models of light propagation as a guiding thread to, well, walk through a very broad field of applications. So I would like to tie applications to each of these topics. This may be more than we have time for, so depending on how we are doing, I may actually skip those parts that I feel have less to do with computational photography and more with, say, physical optics and its understanding. So where do we really start? I think it is a very good idea to start with geometrical optics. Why? Because that's where the computational photography community knows something about these concepts, and that's where everything is very intuitive. So let's think about a simple experiment. I have a laser pointer. There's a source and there's a screen, and well, because we are engineers and scientists, we wrap this in a coordinate system. And for this ray, we know that in every plane along this optical axis, the ray is completely described by its lateral position, its direction, and, well, we can sort of throw in the color as well, so there is a wavelength. And if we take these parameters as a set of generalized coordinates, we can just associate each ray with a point in this artificial space made up by the position and the direction. Well, the direction encoded in a way that looks already ahead to the electromagnetic waves, because this is the usual way we talk about spatial frequencies and how we define them. So this is what I want to call phase space, the phase space of geometrical optics. If we have a bundle of rays, well, each of these rays gives a different point along this axis, so we only change the spatial coordinate, not the direction. Complementary to this is when I have a point source. This is one point in space, and it radiates in all directions. So we have a vertical line here, just one location, all the directions. And of course, if we have 2 point sources, we have 2 of these. So the interesting thing about phase space is that we inject into this whole thing the physics of light propagation. And I want to constrain the discussion here to the paraxial domain. And I have to make comments about the reason why I'm doing this. In this case, talking about geometrical optical rays, I'm doing this because it gives me a link to something very well known and something that, as I have already mentioned, appears in introductory textbooks, ABCD matrix optics. So meaning that if I have a ray and it propagates in space over a certain distance, then it does not change its direction. Of course, it does not, but it changes its lateral position. And if I want to know what my generalized coordinates are doing, this can be expressed by a very simple linear transformation. And these matrices, they are the A, B, C, D matrices of this paraxial ray tracing. So in phase space, what they really tell me is that this one point gets a lateral translation parallel to the spatial axis. In effect, it is, if I have an entire volume in phase space, it is something like a shear. So this becomes a little more evident talking about a point source. If I look at what the rays do over a certain distance, I get now a tilted line. The same with a second point source. So you can think about this as the original 2 lines, and they are now sheared horizontally. If we had something, if we were looking for the analog in a non-paraxial situation, these would not be lines. They would be sort of curves, which does not change things conceptually, but it makes things more difficult. Again, we have sort of a complementary operation, and this is what a thin lens is doing. In this idealized paraxial description, the point in phase space is actually moved in vertical direction. Again, this is in effect a shear operation. Now we have a vertical shear operation that is encoded by this matrix. I think one of the truly important things about phase space optics, and that's something that I think the optics community has ignored for a long time, is how do we actually measure phase space? I mean, much of the literature, I would think up to the 90s, that deal with phase space optics or applications of that, they talk about what phase space is sort of doing and how we can understand things that we have already understood in other ways in this phase space configuration. But to link this with actual applications, we need to measure phase space. Well, let's think about a detector array. And so we can easily measure the lateral position. This is just given by the pixel that is illuminated. We have a certain tolerance here, a certain error in measurement. That's just the pixel size. So how do we throw in the direction? How do we measure the direction? Well, we replace each of the detectors with a micro lens. Again, the micro lens is telling us the lateral position. But now when we move to the focal plane of this, the location of where the ray hits the detector is now encoding the propagation direction. There's a price to be paid, and we should be emphasizing that there is a price. We need more pixels to do this. But what we get from this is now phase space sort of averaged and sampled in this manner. So each of these ellipses is encoding one of the samples that we are getting, and now we have to do something with this. And as it turns out, this kind of phase-space detector is at the very core of very recent developments in 3D imaging and computational photography. And I guess many in this room have seen one or the other application, but I think it is a good way to sort of emphasize the importance here. I think all of you have seen these integral digital printings. I know them since I was a kid. So we sort of look at this image, at this picture from different angles, and we see some movement. And quite obviously, to have this kind of effect, we need to encode more than one image into this sheet. So how is this done? Well, we have in effect our phase space detector. So we have the different images that we want to encode. We slice them, and we interlace them and put them behind a microlens array. So depending on the angle from which we are viewing this, we pick up the slices from one image or from the other image. And, well, that gives us sort of this nice effect. So this is nothing new. This is very old technology, if you like. But of course, if I encode the two images that I need for a three-dimensional image, I can use this for 3D display technology. And that's exactly what you can find on websites right now. Cell phones, computer monitors, and the new gaming console. My son is already saving up desperately to get hands on one of these. Not sure to the excitement of his parents, but, well, anyways. What now? Okay. All of this is a very, very old concept, roughly 100 years old. I don't think we have to be embarrassed. I think this is the exciting part about optics, that we have these concepts. We have sort of a very large box with these ideas. And then there is new technology, there are new detector arrays, there are new ways to do these lenslets, and out of a sudden, toys become sort of cutting-edge applications. But I think it's important to remind ourselves that most of these things are not truly new on a basic level. And talking about integral photography, of course, the phase-space detector is also integral part of what is called a plenoptic camera. So we replace our detector array with a phase-space detector, and we can sort of use this to focus after the fact. Or we have this nice Parallax E built into the data that we are recording. This is just one example that I picked up from YouTube. There are more. Mark Levoy has movies there, and some other groups. This is just to demonstrate what we can do with this, focusing after the recording, computational correction of aberrations and motion blur. So how does this work? The concept is always the same. This would be perhaps our distribution of an ideal image. And the image, we have to talk about this a little more, is obtained by actually summing up in vertical direction these ellipses. This is what gives us usually the image. Now, if I'm out of focus, we talked about this, out of focus, that means propagating through free space, means a shear of our phase-space distribution. So now the distribution that we are getting is something like this. And, well, thanks to the computer, we can just take these measurements, plug them back where they belong, and then compute our image. This brings me to radiometry, and this will be brief, but I think also important. I personally never liked radiometry, and that's not because it is so difficult, but it comes along with a historical baggage of really screwed up terminology. I don't think there is another way to say this. And I did never get my head around this until I started to think in terms of phase-space optics. That was for me the moment when I felt, well, actually, that's not so difficult after all. Well, what it really means is that if we have rays, so this may be an extended light source that sends its rays to a finite aperture, this gives us a phase space area for each of the directions, or for the range of directions. We have sort of our bandwidth, and sort of we have the extension of the source. And if we associate each ray with a weight, so we give an amplitude to each ray, then this is really the radiance distribution. This is really this phase space footprint. That's what we associate with radiance. Now, one of the things that are interesting is when we integrate this radiance over the entire source, then we get something that, at least in the terminology of radiometry, is often called intensity or spectral intensity. And what the physical optics community often calls intensity is then the irradiance, that is the integration of the radiance distribution over all the angles. And yes, radiometry makes a difference whether we have sort of a receiving surface or a source that emits the radiation, but I think this is really where all these things come together and start to make sense. And we have to understand that the irradiance is usually what we capture with a detector. So we measure irradiance. There is a interesting twist to this, a very, very interesting twist. And this is if we just look at a generic imaging system and we think about an imaging system that magnifies or demagnifies our object, then we see that the magnification or demagnification is just the inverse for the range of angles that pass through this system and come from the source and reach the image. What this means is that in phase space we really do not change the size of this area, we merely rearrange everything. And we can go one step further and say, well, if we have a point here with that represents a certain radiance, that radiance is not changed, it is merely located at a different position in this phase space. And that's what the constant radiance theorem is all about. And of course that's important because we cannot really change this, with at least not in this geometrical optical setting. So it means we are sort of limited to the amount of energy that we can capture with a classical optical system. It also has some consequences for designing these plenoptic cameras that I would like to highlight. This was sort of the configuration that I used to introduce this, and this may just be the phase space of this. But typically these lenslets are relatively big. So if we really want to treat them with geometrical optics, they do not give us a good imaging resolution. And this was actually the motivation for this video that I cut down and showed, that we can actually increase this resolution by placing the phase space detector in a slightly different mode. What this means is that, well, we sort of resolve, we have a finer resolution here in X, and because we cannot change the phase space area, something has to give way, and that's, in this case, the resolution that we have in angle. These trade-offs, and I will come back to this when I talk about superresolution, these trade-offs are typically ignored. So there is a kind of tendency in all of these communities to talk about superresolution without really talking about what they want to give up for it. Jim Phenop, one of my very well-known colleagues, once said, "We all want something for nothing." And whenever there's talk about superresolution, we have to take care that we understand what we have to give away. This brings me to the idea of constructing phase space for coherent waves. There is a recent emphasis and push from the computational photography community to sort of not just take what is usually called the light field and add some computation to this, but to take into account the properties of the waves. So how can the concept of the light field be extended to incorporate wave optical phenomena? I think all of these attempts are valuable. Some are brave, but I think they reflect the ad hoc nature of the light field in some sense. And I think it's something that will perhaps turn out to be very useful for practical applications. But I think to sort of have a continuity when we go from the rays to the waves, we need again to take physics into account in a very fundamental way. What I just want to do here, and I think I skip over really the mathematical details, is to highlight the problem that we are facing when we want to deal with waves. Just think about a very generic experiment, Young's double slit experiment, which can be summarized as we have two coherent point sources. So in any diffraction plane behind these point sources, we will find a cosinusoidal irradiance pattern. But let's see what phase space, at least the geometrical optical phase space, is telling us. Well, this is the phase space of two point sources in the plane of these sources. And it tells us that in the far zone, that means that when we look at the spectral intensity, we just add these two lines together, so we have a constant. Regardless of angle, we should see the same thing. The irradiance is fine. We get two spots. But the whole thing becomes more questionable when we look at a diffraction plane. Then the prediction of geometrical optics is that we have a constant in both these projections. Why is this a problem? Because physical optics actually tells us that in the source plane, our spectrum is already modulated. And in any diffraction plane, the irradiance is also modulated in a cosinusoidal way. So the question now is, how can we change our idea about phase space to incorporate these observations? When you look up the joint time frequency transforms, where there is talk about, well, how to set up a joint representation for complex signals. There is often talk about the fact that you can do this in an infinite number of different ways. What I'm arguing here is that if you have certain ideas about the properties of your phase space, for instance, it should describe the complex amplitudes of a coherent optical wave correctly, but it should preserve at the same time all the nice properties that we know from the light fields or the geometrical optical phase space, then we have actually only one choice. To show this would really require us to dive a little bit into the mathematics, and I would like to skip this. The result of this analysis will tell us that we have to amend our phase space in the following way. For our double-slit experiment, the phase space distribution is no longer just this couple of lines, but there is a cosine modulated line right in the center. And if we have this, everything turns out to be correct. We can sort of show that there has to be a line like this from the properties that we ask our phase space to have. And if we generalize this, that means we want a phase space of waves which has the projection properties of radiometry and which incorporates the physics of light propagation in exactly this paraxial mindset that we had for the ABCD matrix optics, then we end up with something that is called the Vigna distribution function. That's how the Vigna distribution function becomes sort of the central distribution for waves in as a phase space representation. And it will be important for us to also talk about the ambiguity function, which is more or less the two-dimensional Fourier transform of the Wigner function. So this is how we construct a phase space of waves. And it is not something that is ad hoc. It's not something that is just sort of nice for computational photography or computational imaging. It becomes a necessity from physics. And I think that makes the whole thing a little cumbersome for computation, but it makes it a lot more satisfying in terms of understanding what is going on in an optical system. So this brings me to what is often called Vigna Optics. Again, here is the definition, and I do not really want to dwell a lot about these equations. One thing that I like to point out is that the original signal, so this is the complex signal that enters into the description, this appears twice, here and here as the complex conjugate. Or here there is an alternative definition. It enters as the Fourier transform and the complex conjugate of the Fourier transform. This is no longer a linear transformation because we have this twice. It's a bilinear transformation. And that is giving everybody a lot of headache because we like linear transformations. Everybody likes linear transformations. And the Wigner function is not giving us this. At least not just like that. It is, however, and this is also different from some alternative representations, it is a unique representation of our signal. We can get the signal back, except for a constant, by inverting this Fourier integral that leads to the Wigner function. We have the projection properties. So this, for instance, is the Wigner function of a rectangle. If we project this in one direction, we get our rectangle. If we project it in the other direction, we get the sinc function squared, the sinc function being the Fourier transform of this. And we need the magnitude squared because, well, we are really looking for something that gives us back the radiometric quantities. So now this is typically associated with the power spectrum, and this for the Fourier optics community is suddenly called intensity. So it's really a screw up in terminology. But here, this is what used to be irradiance. This is spectral intensity. Our invariant is now associated with the space bandwidth product. So again, we can, in a ad hoc way, in a heuristic way, we can associate a signal with a finite space bandwidth product with some footprint in phase space. And this phase space volume is often associated with the number of degrees of freedom, so the number of independent variables that we have to describe our signal. And this should not come as a surprise. The Fresnel diffraction, so that means paraxial light propagation, is described in exactly the same way as before. So there is no change. We can use ray optics in phase space to describe how the Vigna distribution function is changing. This is not something that should be surprising. It is a consequence of the way we constructed this phase space. But it's nevertheless nice to know that this is working. So a vertical shear for parabolic lenses, and now we have other operations. The Fourier transformation is an exchange of space and frequency, so it amounts to a rotation of this phase space. And then there is a generalization that is the so-called fractional Fourier transform in image processing and signal processing, optical signal processing. This plays some role. So this is a rotation of this phase space by an arbitrary angle. In fact, this is, I think, the best way to introduce the fractional Fourier transform. So now we want to talk about applications again. This was sort of the toolbox. Now we have the toolbox for the waves. We want to apply this. So how does this apply? This is an old idea, how to compress the bandwidth of a signal. We can think about two of these phase space transformations. One, for instance, a chirp. That would be the equivalent of actually sending a spatial signal through a lens. So this gives us a shear in vertical direction. And then we use one of these fractional Fourier transformations to rotate the signal back, which gives us, again, a band-limited signal. Why is this band limitation important? Because that's something that we can actually sample and feed into a computer. And it takes us just a little basic algebra to figure out that this bandwidth is actually now reduced. It's a smaller bandwidth. If you think you saved anything, I have to disappoint you. Because if we think about a truncated signal, that's what we usually do. We cannot really sample from minus infinity to plus infinity. We see that the footprint, the area in phase space that we really have to sample with an appropriate sampling rate has really not changed. So the number of samples is the same. We sort of reduce the bandwidth, but it does not save any data points. It should be said that there was a recent surge in publications that try to use these concepts to actually construct sampling theorems, generalized sampling theorems for signals that we could not sample just by invoking the Shannon-Whittaker sampling theorem. And that always works if sort of the phase space of that signal is constrained to some diagonal in phase space. Then we can always sort of transform this back in one way or the other and then apply our standard sampling. There are other generalizations of sampling. I don't have time to really talk about those, but it should be said that they also can be interpreted in phase space. And again, there is it works in very much the same way, in the sense that phase space is not completely covered in all directions. So by transforming phase space in a meaningful way, we get away with a smaller sampling rate, or perhaps with a finite number of samples, where previously we had thought we needed an infinite number of samples. Something very closely related to these sampling theorems is super resolution. And again, I want to sort of just talk about what I would think is the most basic idea about super resolution. And that dates back to Walter Lukács's seminal paper on optical systems with resolving power exceeding the classical limit. So what he thought was that, well, the standard interpretation of an imaging system is that the size of the lens size of the lens aperture, and the focal length, they give us the resolution limit, the diffraction limit, and that's really how far we can go. And what Lukács recognized is that we can think about an imaging system as a communication channel. And if our signal, in one way or the other, does not really fill up this communication channel to its very limit, we can add an encoding step at the front and a decoding step at the end, and we get more data, more meaningful data through this channel than we did before. This requires usually to look for a trade-off. So we can sort of reduce the field of view and increase the spatial bandwidth, or the space bandwidth versus the time bandwidth. And I will mention a few examples a little later. There's one example that is sort of dating back to his paper, or is already in his paper. If we think about a phase space area that we want to squeeze through this type of generic imaging system, so this aperture here, this limits the bandwidth that we have. And now what we want to do is we want to double this bandwidth. So we can put in gratings at two locations, one acting as the encoder and one as the decoder. And in phase space, this means we move our signal to the first grating. This is our shear. Then the grating is actually splitting our wavefront in two copies. And each copy is propagating in a different direction. And if we match this in a good way, then we get the copies lined up this way. One is shifted to the top and one is shifted toward the bottom. We have to squeeze the whole thing through our imaging system, so we cut away part of this. But you recognize that actually everything the signal originally contained is still there. So now we have to go to this second grating. This is in a plane where we have just an image of this. And again, we have a situation where we need to make two copies, one shifted to the top, one shifted to the bottom. And as a result, we get our original signal back. We can back propagate this to an image plane, cut away sort of what we do not really want, and have transmitted a signal with double the bandwidth, but we had to sort of restrict the size of the object. We have had to cut the object size into half. And if you think about this, many imaging applications, they are really based on one or the other of these trade-offs. Digital super resolution, that is usually how to circumvent the finite size of our detectors by, for instance, putting a grid on top of it. In this case, our pixel, the detector pixel, is the communication channel, and the grid that we put on top is the encoder, and the decoder is really software. If we have synthetic aperture radar, we have a trade-off between sort of the bandwidth that our signal is able to register at any given time, and we trade this with the time we need to actually collect all the data. Structured illumination, there we have exactly a situation like this. So usually we have more than just one of these illumination patterns, or there is some other trade-off that we are exploiting. And generalized sampling schemes, like the one that is very popular these days, that is based on sparse sort of signals. And again, we have a trade-off between really how many non-zero locations we have and the resolution that we can get with a reduced number of samples. With Mike Fiddy, I've actually sort of tried to put my head around these super resolution methods not too long ago, and the fruit of our labor got out just last summer. And I think one of the points that I'm making there is the one that I've mentioned previously already, and this is that all of these super resolution methods, they work in one way or the other, but there is in the literature, in the published literature, there is a flavor of, I wouldn't go so far to say dishonesty, but there is a almost deliberate sort of style that ignores the trade-offs. So we always sort of get the message, there is a method that gives me a better resolution. Usually what we have to give up for this is not clearly outlined. It may sometimes be very obvious, but sometimes it is very much hidden. And I have come to believe only in those methods that clearly state why they think the super resolution is working. There are no miracle cures. And I think the phase space analysis shows this very explicitly. I want to change gear and actually talk about something that is closely connected to how we constructed this phase space, and that's phase-space tomography. This is the counterpart for waves of the phase space detector where we started. For the waves, we have to put in a little more effort to really reconstruct phase space, and from the phase space, our signals. Phase-space tomography is usually discussed as one deterministic phase retrieval method. So we have a wavefront, and usually we can only measure the irradiance. There are ways to measure the phase of a coherent signal, like interferometry or holography. And there are certain computational phase retrieval methods to get the phase back. This is a very important application for for instance, to find aberrations of imaging systems. For instance, the corrections of the aberrations of the Hubble telescope involved certain phase retrieval methods. Phase-space tomography is one way to do this. And it is, well, most easily explained by talking about or by connecting it with a fractional Fourier transformer. So let's think we have a wavefront. This is stationary. It's not changing in time. And we can measure this as often as we want. So we have a fractional Fourier transformer. And remember, this is a rotation angle in phase space. And we repeat this measurement with different fractional orders. So what this means is we measure phase space for different rotation angles of our signal. So in each case, we sort of have a projection. And what we end up with is a situation where this is phase space, and we get projections from all directions. And well, now it is a small step to use the concepts of projection tomography, a linear operation, to recover phase space, and from phase space, whatever we want, the irradiance distribution or the coherent signal. There are a few remarks here to be made. First of all, we need really a lot of these projections. So we have a high price to pay to turn the inherently nonlinear problem of phase retrieval into a linear problem of projection tomography. And in some instances, that price may be really too high. So we have to think about this. This is a method that came out, I think, most people see this as something that came out of quantum physics. There were actually some precursors in optics, and I'm pretty proud of this. That it was actually optics that thought about this first. One remark here that will be important in just a few moments, that of course, because we have projection tomography, one of these projections of the Vigna function of our phase-space distribution that we were talking about here is just one slice in the Fourier space of this, and the Fourier space of the Vigna function is the ambiguity function. So when we talk about measuring the irradiance in one of the planes, this is a slice in this plane. And I should also say that the fractional Fourier transform is not essential. We can easily see from a phase space representation that if we want a projection along this line, we can either sort of rotate our distribution and then measure the irradiance, or we can shear this distribution. That means we can just do a free space propagation and do the integration. Both works with some differences, but the concept remains the same. So this is a number of sort of important publications. This is where people usually think about or think that it started, but I think this is a very nice precursor that appeared a few years before that. So one application of phase-space tomography, it's not entirely obvious that we are talking about an application of this, but it really is part of the fallout of this, is the idea of extending the depth of field with certain optical hardware. So the problem is we want to take an image, and well, depending on what kind of optics we have just one focal plane. This is out of focus, this is out of focus, and we want to get something that has a very, very extended depth of field from one shot. The dilemma is the following. We can actually improve the depth of field by just closing the aperture, but that means the light throughput goes down, actually with a square of the f number, and the resolution goes down. So do we have alternatives? To understand the concept, we have to actually just say a few words about aberration theory and what defocus means in this framework. If we look for an out-of-focus object or image, it really means that compared to the in-focus image, we sort of change our aperture function. That's sort of the amplitude distribution where the lens is. And what we do is we add some phase distribution, some quadratic phase. That's how we can describe out of focus. So when the complex amplitude changes, the optical transfer function, that means the autocorrelation of this complex amplitude changes. So this is at least for a two-dimensional system, this is the ideal OTF. It is just a linearly decreasing, so a triangular distribution, triangular function, and the out-of-focus OTF looks something like this. Now, we could think about recording an image with this OTF and then using some sort of inverse filter, but that does still not mean that we have an extended depth of field, and it does present a lot of difficulties where this transfer function gets to 0. We cannot really invert this easily. And here is what we have to remember. The OTF is really the Fourier transform of the image plane irradiance. And at the same time, the Fourier transform of the irradiance is a slice of the ambiguity function. That's where we take from phase-space tomography. That's where we make use of this. And this means simply that the OTF is a slice of the ambiguity function. And if we think not about one defocus plane, but about all of them, then it means the ambiguity function is actually a polar display of all the OTFs with a defocus. So this is sort of the ambiguity function for a rectangular aperture. And if we slice this in this direction, we actually get our perfect triangular shape. And if we slice it in another direction, which corresponds to some degree of defocus, we get the other distribution. So what is the goal that we want to achieve by sort of designing a different system? We want to get an OTF that is more or less constant over a certain range of defocus. There's a two-step process then involved. We get an image with this type of OTF distribution, and then we can impose a simple inverse filter to straighten this out. There's a price to be paid. You can see that this goes to 0 more rapidly than this OTF. So if we sort of think about noise, I don't think we have any hope to really getting this back entirely. So there is a limitation, but it can be used to at least improve the whole problem significantly. This is sort of the first idea to make this happen. Ed Dovsky, who will actually speak at this conference, I think on Sunday. And so he came up with this cubic faceplate. And this gives us this type of OTF, where regardless how we slice this, the cross-section looks more or less the same. And because of this curious shape, this has also been termed the bow tie effect. Again, these are a few of the publications that sort of come to mind in this context. And I think this is a wonderful application actually to show that phase space may not be the final framework to actually implement the algorithm, but it is a perfect way to conceptualize certain problems. Wavefront sensing. This actually ties in with phase retrieval again, but in a slightly different way. There is something to measure the wavefront, which is called the Schack-Hartmann sensor. And a fool who does not recognize that we have, again, a phase space detector. Again, we have a lancelet array. We have sort of our wavefront, and each of the lancelets is sampling the wavefront in a way that we can approximate the wavefront across the lens aperture as a plane wave with a certain tilt. And the tilt leads to a focal point somewhere in the detector plane. And that's a way to measure wavefronts. So the idea here to plug this into phase space is we have our complex amplitude, which is really a phase function. And because it is smooth, we can treat this almost like a geometrical optical problem. So what we measure here is really a local frequency distribution. And for this type of phase function, the corresponding Vigna function is a delta line in phase space. And this first order derivative of the phase is just our local frequency distribution. So the phase space of a Schack-Hartmann sensor looks like this. It is just a line, and again, each lancelet and each detector, and the detector array, they form again a pattern in phase space. And depending where this line goes through, we get sort of a click, and where it does not go through, we have nothing. And that's how we sort of reconstruct the wavefront by going back here. So we realize what we really measure is the first order derivative of the phase. We have to integrate this, and then we get our wavefront back. There are some comments, and those comments will allow me to sort of skip the next section on partial coherence, which is probably too technical in many ways. What is amazing here is that we have this coherent wave and that is actually occupying just a line in phase space. Well, when we think back about geometrical optics, where we started, we really have a complete distribution here. And what I think is the remarkable thing is that we talk about quasi-geometrical approximations here, but we still think about this as a coherent problem. So it means that we have a coherent wavefront, and indeed for a perfectly coherent wave, our phase space carries a lot of redundancy in many ways. It is just when we go to incoherent signals, like the ones that we have in a photo camera, that we really need to deal with this entire phase space, and it makes sense to do so. We really need to sample the entire phase space to understand what is going on. While in many ways, when we have a coherent wavefront, this is not necessary. The same applies actually for for partially coherent signals. Again, this is the entire phase space that we are that we need to really capture the signal entirely. And this is actually something that I like to highlight, that this is the Wigner function, this is the ambiguity function. They are connected by a two-dimensional Fourier transform relationship. This is the mutual coherence function. I didn't do anything. And I'm not sure. It is. I think the laptop is fine and well. I think it is this guy. Is this the one that?
I think the projector turns off after several hours, but
oh.
It should be that. Yeah. Maybe it's too many talks.
Too many talks.
It's shutting down.
No, it has to cool down. So if you have questions, that would be
I think, well, how long do you think it takes to cool down? 5 minutes or something like this? Or?
Yeah, this is usually 3 to 4 minutes.
Okay.
Yeah.
So I think I can explain this slide or the essence of what I wanted to say without the slide. And then maybe we can do the questions that have come up so far, and the last 5 minutes I may have a chance to sort of wrap this up. So I think the important part of this slide is that there is a Fourier transform relationship both with the Vigna function and the ambiguity function with respect to the mutual coherence and the mutual and the sort of the Fourier transform of this. So what I'm trying to emphasize here is that the Vigna function is sometimes brandished as a signal representation that blows up the problem. In particular in physical optics, when people think about coherent signals, well, we have a one-dimensional complex amplitude. Why on earth do you want to put this in a two-dimensional space? You're blowing up this problem. There is a lot of redundancy. Why do you even want to deal with this? Once you come to computation, you are out of control with the data that you have to handle. And this criticism is justified as long as we really talk about a complex amplitude signal. However, at the moment when we go from truly coherent signals to partially coherent signals, in physical optics, the appropriate, I hope I pushed the right button. Ah, good. The appropriate way to describe a signal is really the mutual coherence function. And that mutual coherence function is already two-dimensional for a one-dimensional signal. Why? Because we really have to probe all the pairs of points in space with respect to their coherence properties. And the Vigna function is really just a different way to display this. So in effect, if we really want to deal with partially coherent signals, and that's what we actually do when we do photography, the Wigner function is really capturing all the information, not really the intensity. The intensity or irradiance is giving us the idea that we have a one-dimensional signal, but in reality our information is really already two-dimensional. I want to sort of close this with some notes about the discrete phase space representations. There is a lot of confusion about how to discretize phase space. And I would really like to start that this is not a problem of the computational photography community. Not yet. As long as you stay with geometrical optics and the light fields, well, you have your phase space detector, and that probably does the job. You have to be a little careful about sort of matching all the different components, but you probably do everything right if you think about a spatial bandwidth and you apply the Nyquist theorem. Sampling the Vigna function is a different matter altogether. You need additional sampling points, and you need to do zero padding, and this is a bit of a mess. And I would argue that this is a problem around for several decades now, and there is maybe just a few publications that really drill to the core of the problem. So what is the problem? If we think about the discrete Fourier transformation, the mindset is the following. There is one class of functions for which the discrete Fourier transform is more or less identical to what we get out of the integral transform, and that's the class of band-limited and periodic functions. So if we have a band-limited and periodic function and we sample this, well, we have the original band width, and the sampling is kind of making these copies in all directions. So we have n number of samples per period in one domain, and we end up with n number of samples in the other domain. And in this case, we really take sort of samples of the signal. We do not really mess around with a band, with a frequency band here. We just make sort of copies. So we can get our original function back very neatly by just low-pass filtering this. If we have a truncated non-periodic signal, we introduce some errors. But this is the model that helps us to understand where we are actually screwing up. To understand the problem with the Vigna function, it is a good idea to think about the sampling function or the comp function and what the corresponding Vigna function is. If we think about the comp function as a set of delta points with a distance d from one delta to the next, we know that its Fourier transformation is again a delta comp. And so we would expect that there is really a delta comp distribution in phase space with sort of the same spacing in both coordinates. In reality, we get cross terms due to the bilinear nature of the Vigna function. So interlaced with the expected grid is a grid of delta functions with alternating sign. So something is sort of always there in the middle. And as a consequence of this, if we look for the Vigna function of discrete periodic signals, band-limited discrete periodic signals, it has this kind of shape. It is replicated in x and nu. Okay, we sort of expect this. But the number of samples that we need to represent this is not just n squared, but it is 4 times n squared because of all the bilinear interference terms that are there. And I think this has to be taken seriously, because if the Vigna function is really the basis for computation, this may be a problem too hard to chew on, in particular if we think not about a one-dimensional signal and a two-dimensional Vigna function, but a two-dimensional signal and a four-dimensional Vigna function. So we run out of everything that a computer can give us very easily. The problem is, well, we are not at the end with problems. So if we think about a truncated band-limited signal, so we approximately describe this as this area in phase space. It's good enough to deal with this. Then we have a replication of this based on sort of the expected linear terms, but our interference terms of the Wigner function give us additional copies that are sort of interlaced in this way. So if we sort of fill up this space completely, we get aliasing all around. And that's very well described in the literature. It just never it often is derived in a very formal way. It does not usually pop up as a consequence of going from the periodic to the non-periodic truncated case. So what is the solution? We need to oversample our signal by a factor of 2. That cuts the bandwidth in half. And we have to zero pad the signal. So everything lives in this area in the middle where there is no overlap. It does not really, these two steps do not really increase the number of sampling points that we have in the end, because in the end we really have to deal only with a quarter of all the points in this domain. So these would be the rules to deal with a Wigner function inside a computer. Oversample by a factor of 2, zero padding by a factor of 2. Use 1/4 of the discrete Wigner function to approximate non-periodic signals. I'm not sure that's absolutely attractive. And I hate to sort of close with a negative note. I think that it has to be taken into account because these questions have to be asked. It may mean that the strength of phase-space optics is really in conceptualizing problems, in particular for coherent and partially coherent signals, and then deal with them in whatever is the most efficient way. I think the core of this message, and I hope this has become evident from the examples that I've discussed, is that there are numerous applications that we would usually not sort of tie to these concepts of phase space or joint time frequency transforms, but they have become part of this universe. And I think the reason is that we now have the freedom to do many of these things computationally. So even if we do not sort of reach directly into phase space and have a direct representation inside the computer, we implicitly use these ideas to do our image processing. And I think that's sort of the end of it. These are, I think, useful publications, textbooks in part, collections of important papers that I think will help anybody who wants to dive deeper into the details of phase-space optics. And I thank you very much for your attention.
Thank you. So I hope there are a couple of questions.
Well, I think now is coffee break, so I'm happy to do this over coffee. But yes?
1 or 2 questions.
Yes?
I think it's clear from your presentation that, as computational photography people, we need to borrow a lot from optics and so on. Most of these concepts were there in 1900s, and that's what you said. So what is your advice for a starting student who is going to dabble into computational photography? What does he need to understand? So there's a lot to digest here. Right?
Absolutely. Well, I probably reiterate a little bit of what I've said before, but if you just think about, say, 15 years back, there was a tendency to sort of look at sort of optical hardware and computational methods as two different universes. I mean, I remember sort of ideas, or I think a kind of a competition between the optics hardware guys and the sort of people in computer engineering, I mean, to do robot vision. Right? I mean, the one community would emphasize, there are things like optical correlators. You can do you can sort of cast everything into optical hardware and then do a little post-processing. And I mean, the computer guys, they would just, well, take a camera off the shelf, put it someplace, and then say, oh, we can do all of this inside a computer. And I mean, I think over the past decade or so, these two universes have come together. Ravi is one of the persons who I think strongly promote this concept of sort of merging the hardware side with the software side and bringing these two together. So I think it really depends on how much hardware do you need for your application. I think the more optical hardware you want to include in your overall design, the more you need these kind of physics-based concepts. It does not help you to say, okay, yes, I have a camera here and I understand roughly what the lenslets are doing. You may end up with an application like where you really require a lot of resolution. You have to deal with the diffraction limit. There is no way around this. And then you may consider going deeper into phase space than just the geometrical optical light field. And I think that's where, well, where do the students start? Well, I don't know. I mean, read one of the books. I think what I find interesting, this one by Isakdas and Zalewski and Kutai, it's actually about the fractional Fourier transform, but it provides, for me, one of the best little introductions into phase space. This one is very mathematically oriented. So, well, if you have a student who really loves mathematics, that's the way to go. I think there is still a lack or kind of room for a textbook that is, I mean, I think the phase space optics is burdened with the fact that many who try to write something about it come either from quantum mechanics or they want to show how nice it is that it has something to do with quantum mechanics. And then there comes all the formalism that the theoretical physicists have. I think what has not happened yet is that somebody has written a textbook that is just for us engineers who really want to do things and don't care so much that it has the deep, deep, deep meaning in theoretical physics. Yes?
So in the beginning of your slides, you have the XV kind of space. And
yes.
There was the lambda, which you kind of ignored.
Right. Well, I didn't ignore it. I mean, the reason why it came in was really just that later on you have spatial frequencies. And the spatial frequency is just defined as sort of the propagation angle of a plane wave, taking the sine of this, dividing it by the wavelength. And to sort of have one homogeneous representation for the rays and the waves, I sort of just started with what you usually call a spatial frequency. But it is just a different way to express the propagation direction.
But when you consider the three-dimension, I mean, if you now take the XV and the wavelength, would that...
Well, here you go. Here you go. This is exactly what is not the physical kind of thing. This is where sort of I flinch a little bit when I see this. I understand that when you do computational applications, when you really just care about the computation in one way or the other, you just fill a data cube that fits your problem. But what is really the message here is that if you concentrate on this space of position and spatial frequency, it has a physical meaning. And this physical meaning carries through from geometrical optics to sort of radiometry and partial coherence. And if I add just artificially yet another dimension, this may be something you want to do. Like what you could do is you could add a time dimension and a time frequency dimension. That's still phase space. You still have sort of this physical meaning, but just sort of ad hoc adding a wavelength is not, that's not phase space. It may be useful, but it's not phase space.
It's only a scaling factor.
Yes. And I'm not saying this is wrong. I'm just saying it's not quite what I had on my mind. Yes? I mean, we can have coffee, and anybody who is too shy to ask now can just ask me over a coffee.
So thanks again.
So the coffee is just outside here, but I guess
Presentation be available.
everybody goes there.